Hey, welcome back. This is a review for the first test in differential equations. So I'll be taking questions, basically making questions similar to the questions from your homework. So in particular, problems like 6 to 12 and 1.1. So these are the WebAssign numbers, not the actual numbers from the book. Okay, so then 1.2, questions 1 to 6, and then 8 to 13. 1.3, I'm not going to put any from 1.3 on the test. 2.1, questions like 1 to 14. 2.2, 1 to 14 again. 2.3, questions like 1 to 20. 2.4, 1 to 14. And then 2.6, 1 or 3 to 5. Okay, so with this review, I just want to go into the WebAssign and do maybe 1 or 2 problems from each section, but any of those problems are fair game. And hopefully it'll remind you, okay, I need to do this or this, and okay. So anyways, let's look at 1.1, where we were introduced to a lot of definitions. I'm going to presume you can identify the order and linearity of a differential equation and start with problems like 6 to 12. And in these problems, what we're doing, we were verifying solutions to differential equations. The way that you have to do it in the homework is a little different than what you would probably do on a test. So let me just, I guess, go through an example here. I don't want to do anything too crazy. Let's try, well, I guess they all look kind of nasty. Let's try, this one doesn't look so bad. So let's try number 7. And I'll give you a differential equation of some sorts, and then a potential solution. And you have to determine if this satisfies the differential equation. Okay, so the way the book has you do it is kind of you work on the left-hand side and the right-hand side, and you show that they're the same, right? So in order to pull this off, I can use the given solution to generate derivatives or solve for constants. Okay, so the first derivative y prime, the derivative 8/5 is 0, the derivative negative 8/5 e to negative 30t is negative 8/5 e to the negative 30t times the derivative of the exponent, which will be negative 30. Multiplying out and simplifying a little bit, looks like we're going to get 48 e to the negative 30t. Okay, so I would expect you to kind of label left-hand side, and then over here, I guess, label the right-hand side, and basically show that they're the same. So I'm talking about the left-hand side of the differential equation, which is right here. Let me put it in a different color. This is the left-hand side, and then the right-hand side is right here. Okay, so I'll start on the left-hand side over here. So dy, I rewrite the left-hand side, dy over dt plus 30y. Okay. And then I'm using the given information, and I'm hoping to connect that to the right-hand side, make that equal the right-hand side. So I can replace dy over dt with the first derivative that I found. It's 48 e to negative 30t plus 30, and then times y, and y is 8/5 minus 8/5 e to negative 30t. Okay, I'm going to simplify that material. So 48 e to negative 30t plus, I want to distribute, 5 will go in the 30, 6 times 8 is 48, and then minus, that will be 48 e to negative 30t. And then that will equal, these will cancel, and it will equal 48. Okay. On the right-hand side, there's nothing to really simplify or anything to do there. It's just 48. So we note the left-hand side equals the right-hand side, and so the function is a solution. To the differential equation, or DE, if you wish. Okay. Okay, so just verifying solutions, it's kind of how I want to see it on the test. You got the left hand, you got the right hand, make them equal, and you're good. We talked about the interval of definition in this section. Interval of definition, you have to make sure that the original function is defined and the derivatives are continuous. And on that common interval, you find the interval of definition. And that can be different than the actual domain of the function. So you'll see problems like number 9. So let's take a look at number 9. We're given the differential equation, y minus x times y prime equals y minus x plus 2. And then the solution here, y equals x plus 2 square root of x plus 5. And this first part, you see what you're doing is just making sure it satisfies the differential equation. Read my directions. I may not necessarily need you to do that, but just make sure you're reading directions and doing what I want you to do. If I need you to satisfy show that it satisfies the differential equation, you'll have to, get the derivative here. So y prime. Let me rewrite this first before I do the derivative. It's 2 times x plus 5 to the 1/2. So y prime is 1 plus 2 times the power rule, bring down the 1/2. You got x plus 5 then to the negative 1/2. And so we can then work accordingly, showing it satisfies the differential equation. So this would be a left-hand side, right-hand side scenario. On the left-hand side, you have y minus x times y prime. So we can write that out using the given information. X plus 2 square root x plus 5 minus x times our derivative. 1 plus, will be 1 all over square root x plus 5. Simplifying x minus x, those will cancel, and you'll have 2 square root x plus 5 times 1 plus 1 over square root of x plus 5. Distribute, you get 2 square root of x plus 5 plus, I guess, just 2. And then let's work with the right-hand side and see if we can connect the sides together. So y minus x plus 2, you could write it as x plus 2 times x plus 5 to the 1/2 minus x and then plus 2. And of course you get the x's canceling, and then you have 2 square root x plus 5 plus 2. So the right-hand and left-hand sides are the same. So the solution, the function given, I should say function, satisfies the differential equation. Then we're after figuring out the interval of definition. So you can find the actual domain of the function. So the domain of f of x, that's just going to be where you're not having negatives under the square root, because the function is y equals x plus 2 square root of x plus 5. The only issue is that square root. Right, so you need to ensure that x plus 5 is greater than or equal to 0. In other words, x is greater than or equal to negative 5. So the domain is actually from negative 5 to infinity. Okay, the interval of definition then, which I'll just title I, is the overlap between the domain of the function and the domain of its derivative. So we already know the domain of the function. Let's work with the domain of the derivative. So, and not just the domain, but where is it continuous? And we're not going to use several intervals, just one interval where it's continuous. Okay, so in this case, y prime, I could just borrow that from above. It'll be 1 plus 1 all over the square root of x plus 5. And this function, you need to make sure that x plus 5 is greater than 0. strictly greater than 0, because if you let it equal 0, you could have division by 0 in the denominator of this fraction, right? So I need x plus 5 to be greater than 0. In other words, I need x to be greater than -5. That's where this function will be continuous. So the actual interval of definition then, which you call I, will be all numbers greater than -5. So -5 to infinity. Okay? So be able to, and from this section, be able to show that a given function satisfies a differential equation and be able to identify the domain of the function and the interval of definition. Okay? So there's a couple, one or two versions of that problem, and then so on and so forth. Okay, let's move on to 1.2. So 1.2, we were finding particular solutions to initial value problems. Again, you may be called upon to determine the interval of definition. If there's more than one interval, it'll be the interval that includes the initial value. So for example, all right, so we're in 1.2 now. For example, problem 2, they're giving you the differential equation y prime plus 2xy squared is 0. We don't necessarily even need that, but let's see what else it goes. So the solution, 1 all over x squared plus c, and then the initial condition y of 3 equals 1/5. Okay. All right. So it doesn't seem they even really are asking for the interval of definition in this case, but yeah, we'll go ahead and get it. Okay. First, let's get the particular solution. So you use the initial value to get the particular solution. So this part right here is x, and then this part right here is your y. So let y equal 1/5, and on the other side you're letting x equal 3. So 3 squared is 9 plus c, cross multiply, 9 plus c is 5. So c will be -4, and our solution y equals 1 all over x squared minus 4. Okay. The domain of this function, the domain is just going to be, let's see, everywhere the denominator is not 0. Okay, so negative infinity all the way up to, and if you need to, go down here and solve this equation. X squared minus 4 is 0, so x is equal to 4. X squared is equal to 4, so x is plus or minus 2. We have to omit those from the domain. So negative infinity to -2, union with -2 to the 2, union with 2 to infinity. Okay. For the interval of definition, I mean, if that's what they're asking for, which it seems like that's what they're asking for, you also need to make sure then the derivative works in your particular interval. So let's rewrite this as x squared minus 4 to the -1. The derivative there would be negative x squared minus 4 to the -2 times 2x. And its domain is exactly the same as the previous functions. So basically this thing is continuous everywhere that the denominator is equal to 0. And that happens when x squared minus 4 is equal to 0. In other words, when x is equal to plus or minus 2. Okay. So again, the interval of definition is going to be taken from this set of intervals. Now, the interval of definition is just one interval, so you have to pick the correct interval. And for us, then, the interval in an initial value problem will be the interval where your initial value is. Okay, so our initial value is x equals 3. That means that we're going to be in this rightmost interval from 2 to infinity. Okay. Okay, so you should be able to get the initial, get the solution given the initial condition, and then if I ask for it, you should be able to identify the interval of definition, the largest interval I over which the solution is defined. Okay. So most of these are pretty much the same. Maybe they give you extra. Let's look at number 6, I guess. We have the differential equation, which again is you kind of don't need the differential equation. Y double prime minus y is 0. The general solution, c1 e to the x plus c2 e to the negative x, and then the initial conditions, c of -1 equals 2, and then y prime of -1 equals -2. Okay, so I need to get the derivative from this thing. Y prime will be c1, the derivative e to the x, then plus c2 e to the negative x times -1. So I just put the negative out in front like that. Then you could plug the initial conditions into these two things and solve for the constants. Okay, so first I'll use the y of -1 equals 2 in this equation, y equals c1 e to the x plus c2 e to the negative x. Right? So plug 2 in for y, and then you have c1 e to the -1 plus c2 e to the -1 will just be 1. Okay, so got 1 like that. Then let's get the other guy going as well. So y prime of -1 is -2. So I plug that into the equation, y prime equals c1 e to the x minus c2 e to the negative x. I get -2 equals c1 e to the -1 minus c2 e to the 1. You can do substitution here. It might be easier to just do the addition method. So what I would probably do is take the two equations and add them together. So if you take this character and just add it column-wise, so c1 e to the -1 minus c2 e to the 1. 2 minus 2 is going to give you 0, and then you'll have c1 e to the -1 plus c1 e to the -1. That's 2 c1s e to the -1. And then you could solve for c by dividing both sides by 2 e to the -1. You just end up with c1 being 0. Okay. Then you could take that and plop it into this equation. So you get -2 equals 0 minus c2 e to the 1, and solve for c2. So you get c2e equals 2, and then c2 must be 2 all over e. Okay. Then finally form your solution by back substitution into the original equation. So the original equation is, where is it at? It's right here. Your general solution. That's also right here. So I'm not going to be able to see it because I'm kind of scrolled down so far. So I just plug my C1, C2 into this thing. Right. So I'll end up with y equals 0 plus C2, which is 2 all over e times e to the negative x. Here you write it, make it look pretty. 2e to the -1, e to the negative x, and then just add the exponents. So 2e to the -1 plus negative x. That's what you see in my solution there. One other thing we had in this section I almost forgot was the interval of, or rather the region of the plane where there's a unique solution. And that happens when your f of xy is continuous and also your partial of f with respect to y is continuous. So, for example, number 8, our f of xy is the dy over dx. Okay, so that's y to the 2/3. This thing is continuous everywhere. So right now it's the whole xy plane. So this is your f of xy, by the way. Then you just take the partial of that with respect to y. Power rule, bring down the 2/3. Y to the 2/3 minus 3/3 is -1/3. And then that's going to create an issue. All right, so you got 2 all over 3 times the cube root of y. You can have negatives in the cube root, but you can't let y equal 0. So there will be a unique solution anywhere such that y is not equal to 0. So there will be a unique solution so long as y does not equal 0. Okay. Okay. So make sure you kind of, if you've forgotten about that stuff, make sure you go through and rehearse that a bit. Let's move on to 1.3 then. Oh, I didn't put 1.3 on the test. So 1.3 was just kind of an introduction to modeling. Let's move on to 2.1. We'll return the modeling in chapter 3. And there you're actually going to be solving the differential equations associated with the models that you would be creating in 1.3. So we're going to see it again, and I'll put it on the next test. So anyways, you should be able to kind of fabricate differential fields. So this is 2.1. 2.1. Within reason. I'm not going to ask you to do like a computer picture like they have. I may just ask you to do the differential field for, or the slope field rather, for the a set of points around the origin, right? So, for instance, if you have, you're going to make a t-table, and then you have your dy over dx. So say like -1, -1, and then -1, 0, and then -1, 1, and then 0, -1, 0, 0, 0, 1, 1, -1, 1, 0, 1, 1. Okay, and then you plop those into your differential equation. -1 squared is 1 minus -1 squared. That's just 1 minus 1 is 0. This would be 1. This would be 0 again. This would be -1. This would be 0. This would be -1 again. This would be 0. This would be 1. And then finally this one would go back to 0. Okay, and you should be able to plot the little tick marks that represent the slopes of the tangent line to the solution curves going through those particular points. Okay, so -1, -1, the slope is 0. Let's put it in a different color. 0, and then up 1 over 1, and then 0. And then 0, -1, when we're going down 1 over 1, 0, 0, 0, and then down 1 over 1. 1, -1 is 0, and then it's up 1 over 1, and then 0 again. So you should be able to zip through and produce a little slope field for me. And then if I want to, a particular solution, we'll say going through this point here, you should kind of be able to maybe just kind of sketch something in. It doesn't have to be perfect. Okay. Okie dokie. So stuff like that. There's a ton of these. Is there anything else in here? Oh yeah, phase portraits. So you should be able to do phase portraits and then identify the points as stable or unstable or semi-stable, and then draw some solutions. So let's try number 9. I don't put video quizzes in the review videos, so don't worry about that. I figure you should be watching it. If not, that is your choice. Okay, so here's a differential equation for the phase portrait. You need to find where that's equal to 0. So you just set it equal to 0 and solve. So y equals 0, y equals 4, and then you do your phase portrait. So you just draw a line and put 0 and 4 on it. And then get the sign of the differential equation in these regions. And then to the side, I'm going to leave some room for potential solutions. So there's basically 3 regions. And the top region, you do a test value, like you put 5 into this equation and see if it's negative or positive. 5 will give you a positive value. Positive times positive is positive. So it will be going up in that region. So potential solutions, if you want to, you could draw one like that. In the middle, at like 3, you'll have a positive times a negative, so it will be going downwards. And potential solution like that. Try -5, negative times a negative will be positive. So the point 4 is going to be unstable. The point 0 will be stable. And then we have some pictures of the typical solution curves. Oops, I lost one. Okay. All right. Let's see. That's pretty much it in this section. Let's move on then to 2.2. Let's see what we're dealing with there. So 2.2. So these are doing separation of variables. You should be able to do pretty much any of these characters. Let's look at number 6, I guess. So you have cosecant y dx plus secant squared x dy equals 0. This kind of looks like an exact equation, right? But we're gonna, I will say the direction solved by separation of variables. And so you will have to do that method. So anyways, I'm gonna get dy over dx by dividing everything by dx. So I got cosecant y plus secant squared x dy over dx, 0. Move the cosecant to the other side so you can separate. Dy over dx equals negative cosecant y. Divide both sides by secant squared, divide both sides by positive cosecant. I like to keep those constants on the right side. And then move the dx over as well. I guess I could have just kept the dx there. Oh well. So dividing both sides by cosecant, 1 over cosecant is the same as sine, so I'm going to have sine y dy eventually. On the other side, negative 1 over secant is cosine, so negative cosine squared x dx. Then I can go ahead and integrate these things. The integral of sine of y is negative cosine y, and on the right, I may have to do a little bit of memory work here. Cosine squared is 1 plus cosine of 2x all over 2. So hopefully you remember all your calc 2 stuff. Negative cosine y equals negative. I'm going to split that into 2 integrals, basically 1/2 and the integral 1/2 and the integral of cosine of 2x over 2. So the first integral there will just give me x over 2. So I have cosine y equals negative x over 2 plus 1/2 integral of cosine of 2x. And I lost a negative there. Negative integral cosine of 2x is going to be sine of 2x over 2. You could do a u sub if you need to, but ultimately it'll just be sine of 2x over 2, and then plus your integration constant. I'm not going to be able to get a nice explicit solution, so I'll just leave it kind of as is. Negative x over 2 minus sine of 2x over 4 plus c. Okay. Yeah, so be able to pull those off, be able to do the initial value problems as well. I won't need you to do the integral solutions to differential equations like number 15. You can not worry about, you don't have to worry about that one. Okay, let's move on then to 2.3. So 2.3, we got integrating factors, right? You also need to be able to identify the interval of definition for these, and that's just the interval such that p of x and f of x are continuous. Okay, so let's try, I guess, number 4. I'm not going to have you identify the transient terms or anything, just the interval definition and the solution. So anyways, x squared y prime plus xy equals 2. This is not in standard form for the first order differential equation. You need the divide by x squared, so we actually have y prime plus y all over x equals 2x squared, or 2x to the negative 2. We note that p of x is 1 over x, and then f of x, of course, is 2 all over x squared. The domain of these things, both of them, is going to go from negative infinity to 0, and then union 0 to infinity. You want to pick, if you're not given an initial value, pick the one on the right in this case. So our interval definition, I, is going to be 0 to infinity. Then go ahead and get your integrating factor. I need to see the integrating factor in your work. You can't just use that solution, you know, like they memorize the big, long, ugly thingamajig that you see. I need the table of contents again. I need to see the process, you know, regardless. So anyways, it's e to the integral of 1 over x dx. That will be e to the ln of x if you pick the 0 to infinity interval, and that will be just plain old x. So then you have to go back and multiply the original, this form, the original form, it has to be in this form, by x. So you get xy prime plus y equals 2x to the negative 1 now. Then you collapse it. It'll always be mu times y. On the other side, 2x to the negative 1. Integrate both sides with respect to x. So on the left, the integral and the derivative cancel. You have xy. On the right, you're doing a power rule. Whoops, you're not, right? Because that's the special, the one integral you can't do the power rule on. That's our natural log integral. So it'll be 2 ln absolute value of x plus c. You could get an explicit solution by dividing both sides by x in this interval. X will not equal 0. So we have 2 ln absolute value of x. And in this interval, you're not necessarily going to need the absolute values there. You can write them in. I'm not going to take off points if you do. But divided by x and then plus c all over x. And again, the constant won't absorb the variable. Okay. All right. So anyways, yeah, even in the solution, they were okay without the absolute value. Let's see x. Okay, so make sure you can handle the integrating factor problems. There's also, was there integrating factor with initial conditions? Yeah, and so the ones with the initial conditions are in here as well. Ooh, and then there's piecewise ones. So let's do the last piecewise problem, problem 20. We have dy all over dx plus 2xy equals f of x, and y of 0 equals 6, and then f of x is given in 2 pieces as x and 0. X when x is in between 0 and 1, and then 0 when it's greater than or equal to 1. So you need to solve 2 differential equations. You start with the one equal to x. The integrating factor here, e to the integral of 2x. So that will be e to the 2x squared over 2, so e to the x squared. Multiply through by that. Collapse that left-hand side. And integrate the right-hand side. We could do a u sub on that. So u is x squared, du is 2x dx. In other words, dx is du all over 2x. So integrate both sides, So then you get e to the x squared y equals, on this side, x e to the u times du all over 2x. Pull out a 1/2 on the right-hand side. And then you'll have just the integral of e to the u. The integral of e to the u is just e to the u, back sub e to the x squared plus c. And then you can divide by e to the x squared, and you get y equals 1/2 plus c e to the negative x squared. Right, we want y of 0 to equal 6. So we use this to solve for c initially, so 6 for y, and then 0 for x. So I get c e to the 0 is just c. And so c will equal 12 halves minus 1 halves is 11 halves. And that will give us the first piece of our solution in our differential equation. Y equals 1/2 plus 11 halves e to the negative x squared. And that will be when x is in between 0 and 1. Then to get the other solution, you solve that that differential equation, but with 0 on the right-hand side. Okay, you use the other piece now. So dy over dx plus 2xy equals 0. Again, the integrating factor you'll find is e to the x squared. Multiply through, you get e to the x squared, dy over dx plus 2xy e to the x squared equals 0. Collapse that left-hand side. Then you're integrating both sides. The integral of 0 is just a constant c, divide. And then you want this thing to equal the same thing as the other equation at that point where the piecewise function goes into the other piece. In other words, at 1, right? So I need y of 1 to equal whatever that other function equals. 1/2 plus 11 halves e to the, it'll be negative 1, and for x squared, 1 squared is just 1, so negative 1. I need, so I need this thing to equal that thing. Okay, so I'll put c all over e to the 1 equals 1/2 plus 11 halves e to the negative 1. Multiply everything by e, you get 1/2 e plus 11 halves, and then plug that back into the equation for your other piece, right? So we'll have 1/2 e plus 11 halves all over e to the x squared. You can multiply top and bottom by 2. And you end up with the other piece, e plus 11 all over 2e to the x squared, which now you can complete the piecewise function here. Plop that in there, you get e plus 11 all over 2 e to the x squared when x is greater than or equal to 1. And then this thing would be your final solution here. Okay, so those are fair game. What else? That's 2.3, 2.4. So 2.4 was the exact equations. I'm not going to do any of the ones where you need to do the integrating factor. So you have to memorize the formulas, and I'm not big on memorizing tons of formulas. So just be able to do these exact problems. Let's try number 11. This has also an initial value to it, so be able to do the ones that have initial values as well. 2xy plus x squared minus 3 dy equals 0. Y of 1 is 1. So y of 1 is equal to 1. So first you have to make sure that the mixed partials are equal. So basically this is your m, this is your n, and you want the partial of m with respect to y to equal the partial of n with respect to x. So the partial of m with respect to y, I'm going to FOIL this guy out first. So x squared plus 2xy plus y squared. So the partial with respect to y is going to be 2x plus 2y. Okay? And then the partial of n with respect to x is 2y plus 2x. So those are the same, so you can go ahead to your process. You're taking the partial with respect to y of the integral of m with respect to x, and that should equal n. Okay, so let me use the FOILed version, the x squared plus 2xy plus y squared dx, and that should equal n xy plus x squared minus 3. Okay, so partial with respect to y of x cubed all over 3 plus 2x squared y all over 2. So it'd just be x squared y plus x y squared plus this function that may have been destroyed by the original derivative with respect to x. And all of that should equal 2xy plus x squared minus 3. Let's take the derivative with respect to y on the left here. So 0, and then x squared, and then 2xy, and then g prime of y should equal 2xy plus x squared minus 3. The 2xy's cancel, the x squares cancel, so you get g prime of y is negative 3. Integrate both sides with respect to y, so g of y equals negative 3y. And so our without the initial condition, we have a general solution, borrowing this information, of x cubed all over 3 plus x squared y plus xy squared minus 3y equals some constant. Now we use the initial condition, y of 1 is 1, to solve for the constant. So you have 1/3 plus 1 minus 3 is c. 1 plus 1 minus 3 is minus 1, c. So 1/3 minus 3/3 equals c. So c is negative 2/3. And so our particular solution, x cubed over 3 plus x squared y plus xy squared minus 3y equals negative 2/3. Okay. Okay, so be able to do those. What was that? Oh, and I'm not putting the integrating factor exact equations on the test. So you don't have to worry about like 15 or 16 or any of these, 17, 18, 19. I think those are all integrating factors, just the normal ones. Okay, finally then 2.6, you should be able to do a couple iterations of Euler's method. I'm not going to have you do like 20 iterations or something crazy like the second problem in this, but you know, having you do like one part where h is equal to 1, that's not beyond me. So let's try number 4, and so like y prime equals x minus y squared, y of 0 is 0.8, and I want you to figure out y of 0.5 using, and I'm not going to have you do something like 0.05, I'll probably just have you do h is 0.1. Okay. So h equals 0.1. So find y of 0.5. Okay, so x sub 0 is 0, y sub 0 will be 0.8. X sub 1, I got to go all the way to 0.5. And use 4 decimal approximations. So 0.1, 0.2, 0.3, 0.4, 0.5. So y sub 1 will be y sub 0 plus h times f of x comma y. So you're basically plugging x0, y0 into y prime. So you get 0 minus 0.8 squared. And then you just go to your calculator. 8 plus 1 times 0 minus 0.8 squared. So 0.864. Y2, 0.864 plus 0.1 times previous x is 0.1 now. 864 squared. Okay. So this 1 times 1 minus answer. Square this. So 4 decimals, 0.9224. I sub 3 is that previous answer plus 0.1 times now 0.2 minus the previous answer squared. So answer plus 0.1 times 0.2 minus previous answer squared. So 0.9746. Y sub 4. Again, the previous answer 3 minus the previous answer squared. It's almost like you could just go in here and edit in your calculator if your calculator is nice enough. So I'm getting about 1.0201. Then y sub 5. 1.0585. Previous answer plus 0.1 times 0.4 minus 0 squared is 1.0585. Okay, so nothing excessive. This is probably more than I want. Maybe just go up to like what is y of 0.3 or something like that, just to make sure you can do the process. And then that'll be it. So hopefully it's pretty straightforward. Yeah, that's about it. Okay, thank you for watching as usual, and we'll see you next time.